Welcome back to the deep dive. Today, we're jumping into the world of Amazon Web Services.
Yeah, specifically the core concepts. We've got some great material here that gives a really good first look at the fundamental building blocks.
Exactly. Our aim is to give you a solid handle on these essential services.
Think of it like a starter kit for AWS. We'll touch on compute, where stuff actually runs, then storage, networking, security, the big ones.
And some of those underlying services too, right? The ones that kind of make it all work together.
Absolutely. Foundational stuff.
So the mission today, break down the key ideas from these sources, make sense of them, and really understand why these AWS services matter.
Okay, let's start with the compute part.
Yeah.
EC2.
EC2, Elastic Compute Cloud. Basically virtual servers. Imagine a computer, but it's running on AWS hardware, not under your desk.
Okay, virtual computers. And they need storage, obviously. The sources mentioned two main types, Instance Store and EBS.
That's right. Instance Store and Elastic Block Storage, EBS. They're quite different. Okay, let's get under the hood of Instance Store first. What's the deal there?
Well, the interesting thing is that Instance Store volumes are physically attached to the host machine running your EC2 instance.
Physically attached so fast.
Incredibly fast.
Yeah.
Because of that direct connection. Great for temporary data, caches, that sort of thing. But here's the kicker.
Oh.
It's ephemeral, non-persistent. Meaning if you stop that EC2 instance, or if it terminates for any reason, boom, data gone, vanishes.
Okay, ephemeral, got it. Super fast, but temporary. Why would you want that? It seems risky.
Well, it has its uses. The sources point out things like root volumes in really distributed systems where instances are designed to be replaced anyway.
Ah, okay. If one fails, you just spin up another one. The data wasn't critical.
Exactly. Or for temporary scratch space, like
Yeah.
processing data quickly where you don't need to keep the results long-term on that specific volume. Think stateless applications managed by auto-scaling, speed and easy replacement.
Makes sense for those kinds of distributed, resilient setups. Okay, so that's Instance Store. What about EBS? Elastic Block Storage. That sounds more permanent.
It is. EBS is persistent block-level storage. Think of it like a virtual hard drive you attach to your EC2 instance.
Persistent being the key word.
Definitely. Data on an EBS volume stays put. Even if you stop or terminate the instance it was attached to, you can detach it, reattach it somewhere else. It persists.
So that's what you'd use for your operating system, your database files, your important application data.
Precisely. Anything you can't afford to lose when an instance stops. EBS is your go-to for reliable, persistent storage for EC2.
Right. Okay, so we've got our virtual server, EC2, and our persistent storage, EBS. How do we actually connect to it, especially a Linux one? The sources mentioned SSH.
Yep, Secure Shell, SSH. It's the standard secure way to get command line access to Linux servers, including EC2 instances.
And the secure part is key, right?
Absolutely crucial. SSH encrypts the entire connection. Your login, the commands you type, the output you see back, file transfers, it's all scrambled and protected over the network, like a secret tunnel.
Okay, a secret tunnel. How does that work? Something about key pair.
Yeah, that's the common way. You generate a key pair,
Yeah,
a private key and a public key.
private and public.
The private key, you keep that secret, like really secret, on your own computer. The public key, you give that to AWS when you launch the instance, and AWS puts it on the EC2 server.
Okay.
So when you try to connect with SSH, your computer uses the private key to prove it has the right credentials. The server checks if it matches the public key it has stored. If they match cryptographically, you're in.
Yeah.
No password needed, usually.
Ah, clever.
Yeah.
So the public key lives on the server. Where?
Typically, yeah. The sources mention it's stored in a file called authorized keys within the .sh directory in the user's home folder on the Linux instance.
Right, dash authorized keys.
Yeah.
Got it. So keep that private key locked down. Now, what if I just need to jump in quickly from the AWS console? I saw something called EC2 Instance Connect.
Ah, yeah, that's a handy AWS feature. Instance Connect lets you SSH in directly from the AWS management console in your browser. Kind of bypasses needing the key file right then and there.
Sounds convenient. Any catches?
A few requirements. The instance needs a public IP address. It usually needs to be running a specific Amazon Linux AMI, or you need to install the Instance Connect package.
Yeah.
And you need the right IAM permissions, of course. Plus, your security group needs to allow SSH traffic from AWS's specific Instance Connect IP ranges.
Okay, so not quite magic, but useful for quick access via the console if you've set it up right.
Exactly. Key pairs for regular, secure, maybe automated access Instance Connect for those quick console sessions.
Makes sense. All right, let's switch gears to networking. How these instances talk to each other and the world. IP addresses, The sources list a few types.
That's right. In AWS, you'll mainly deal with private IPs, public IPs, and elastic IPs, the IPs.
Okay, let's take them one by one. Private IPs.
Private IPs are for internal communication within your AWS network, your VPC. They aren't reachable directly from the public internet.
So server-to-server talk inside my cloud setup.
Exactly. AWS assigns them automatically when you launch an instance, and they stick with the instance until it's terminated. Then the IP goes back into the pool.
Okay. What about public IPs? Sounds like the opposite.
Pretty much. Public IPs are reachable from the internet. AWS can assign one automatically when you launch an instance if you're in a public subnet.
But there's a catch with those too, isn't there?
Yeah, the key thing is, a standard public IP assigned at launch is released if you stop the instance. Not just terminate, but stop. When you start it again, you'll likely get a different public IP.
That could be a problem if something relies on that specific IP address.
It can be. Also, it's worth noting, these public IPs aren't directly on the instance's network interface. There's a translation happening. Network address translation, NAT, usually via the internet gateway associated with your VPC. It maps the instance's private IP to the public IP for outbound traffic and vice versa for inbound.
Okay, so if the standard public IP changes when I stop the instance, how do I get a permanent public IP?
That's where elastic IPs, EIPs, come in. EIPs are static public IP addresses that you allocate to your AWS account. You can then manually associate an EIP with an EC2 instance.
And it sticks.
It sticks. Even if you stop the instance, the EIP remains allocated to your account and associated with that instance, or ready to be associated. When you restart, it keeps the same EIP.
So stable public endpoint. That's useful.
Very. But be aware, AWS charges a small fee for EIPs that are allocated but not associated with a running instance. They want you to use the resources you reserve.
Makes sense. Pay for the parking spot if you're not using it.
Okay.
So private, public, and elastic IPs. And you mentioned NAT letting private instances talk out.
Right. Even an instance with only a private IP can initiate connections out to the internet, like for software updates. The traffic goes through a NAT gateway or an instance configured for NAT, which uses its public IP to talk to the internet and translate the responses back to the private instance. Keeps the private instance from being directly exposed.
Clever. Security through controlled access. Speaking of security, let's talk security groups. The sources describe them as virtual firewalls.
Exactly. Think of them as a firewall attached directly to your EC2 instance, or more precisely, to its network interface. They control what traffic is allowed in and out.
At the instance level. Okay. How do you define the rules?
You create rules based on things like protocol, TCP, UDP, ICMP, port numbers, like port 80 for web traffic, 22 for SSH, and the source or destination of the traffic.
Source or destination? Can that be an IP address?
Yep, IP address ranges like 0.0.00 for anywhere, or just your office IP. Or, and this is really powerful, you can specify another security group ID as the source or destination.
Oh, interesting. So you could say, allow traffic from any instance that has this security group attached.
Exactly. Great for managing communication between tiers of your application without worrying about specific IP addresses changing.
Neat. What else is important about security groups?
Two key things. They are stateful, and they only have allow rules.
Stateful. What does that mean here?
Stateful means if you allow incoming traffic on a certain port, the return traffic for that connection is automatically allowed back out, regardless of your outbound rules. The security group remembers the connection.
Okay. Simplifies things. And only allow rules.
Yep. There are no deny rules in security groups. If no rule explicitly allows the traffic, it's implicitly denied. Default deny.
Got it. So you have to positively permit what you want. Now, the sources mentioned blacklisting versus whitelisting briefly. How does that fit?
It's a general security concept.
Yeah.
Blacklisting means you allow everything except a specific list of bad things. Whitelisting means you deny everything except a specific list of good things.
Whitelisting sounds safer.
Generally, it is. Security groups, by only having allow rules and denying everything else by default, operate on a whitelisting principle. You explicitly allow what's needed.
Makes sense. Now, are security groups the only network firewall in AWS? I thought I read about NACLs too.
You did. Network Access Control Lists, or NACLs. They're another layer.
How are they different?
NACLs operate at the subnet level, not the instance level. Think of them as a firewall for the entire subnet. Also, unlike security groups, NACLs are stateless.
Stateless, so they don't remember connections.
Correct. You need separate inbound and outbound rules for both directions of a connection. If you allow web traffic in on port 80, You also need an outbound rule to allow the response traffic back out on the appropriate ephemeral ports.
More complex then.
A bit more, yeah. And NACLs support both allow and deny rules. They're evaluated in order, lowest number first.
So 2 layers. NACLs at the subnet boundary, stateless, allow, deny, and security groups at the instance level, stateful, allow only.
You got it. You can use both for defense and depth.
Okay, let's shift to protecting the data itself. Encryption. The sources mention AWS Key Management Service, KMS.
Right. KMS is a managed service that makes it easier to create and control the encryption keys used to encrypt your data. Takes away a lot of the headache of managing keys securely yourself.
Managed keys, what kinds are there?
The sources highlight 2 main types: AWS managed keys and customer managed keys, CMKs.
Okay, AWS managed.
With AWS managed keys, AWS handles pretty much everything: creation, rotation, every 3 years automatically. Management. You use them via AWS services, but you don't directly manage the key material itself. Simpler.
And customer managed keys, CMKs.
With CMKs, you have more control. You create them, you manage their policies, you can enable or disable them, schedule them for deletion, and you can opt into automatic rotation every year. You still don't see the raw key material, AWS protects that, but you manage the key's lifecycle and permissions.
So more control maybe for compliance reasons?
Exactly. If you have specific requirements around key management and rotation policies, CMKs give you that flexibility.
Got it. And KMS can generate data keys too. What's that about?
Yeah, that's a common pattern. Instead of encrypting huge amounts of data directly with your main KMS key, you ask KMS to generate a unique data key.
Okay.
KMS gives you back 2 versions of this data key: a plain text version and a version encrypted under your main KMS key, your CMK or AWS managed key.
Right.
You use the plain text data key to encrypt your actual data, say a large file. Then you discard the plain text key and store the encrypted data key alongside your encrypted data.
Ah, I see. So the big data is encrypted with a temporary key.
Exactly. And to decrypt later, you give the encrypted data key back to KMS. KMS uses your main key to decrypt the data key, gives you back the plain text data key, and you use that to decrypt your actual data. It's called envelope encryption. It protects the main key because it's only used to decrypt small data keys.
Envelope encryption. Very cool. Keeps the master key safer. Okay, moving beyond the absolute core compute storage security, the sources list some other foundational services. Let's touch on those. SNS.
Simple notification service. It's a managed pub-sub messaging service. You create topics, applications publish messages to topics, and SNS pushes those messages out to subscribers.
Subscribers like?
Could be other AWS services like Lambda functions, SQS queues, or even things like email addresses, SMS text messages, mobile push notifications. Great for decoupling applications and triggering events, like a digital announcement system.
Okay, broadcasting messages. What about SQS? Simple queue service. Sounds similar.
Similar but different. SQS is a managed message queue service. Applications send messages into a queue, and other applications pull messages out of the queue to process them, usually one at a time.
So not a broadcast, more like a waiting line for tasks.
Exactly. It decouples components, acts as a buffer, improves fault tolerance. If the processor isn't ready, the message just waits safely in the queue. Really good for reliability and scaling.
SNS for broadcast, SQS for queues. Got it. Next up, CloudFront. CDN, right.
Amazon CloudFront is AWS's content delivery network. Its job is to speed up the delivery of your web content static files like images, videos, CSS, JavaScript, but also dynamic content.
How does it speed things up?
It caches copies of your content in edge locations all around the world, physically closer to your users. When a user requests content, CloudFront serves it from the nearest edge location, reducing latency. Much faster for the user.
Edge locations, so faster loading globally, makes sense. What about Route 53, DNS?
Exactly. Route 53 is AWS's domain name system service. Highly available, scalable DNS.
And DNS is?
It translates human-friendly domain names, like www.yourwebsite.com, into the IP addresses that computers actually use to find each other, like the Internet's phone book.
Okay, and Route 53 manages these translations?
Yeah, using hosted zones. You create records in a hosted zone, like an A record, mapping your domain name to an IP address, maybe the IP address of your web server, or a CloudFront distribution. It supports public hosted zones for the public internet and private hosted zones for DNS within your VPCs.
So Route 53 points the domain name to the right AWS resource's IP address. Crucial. Okay, last foundational service on the list. RDS databases.
Right, Amazon Relational Database Service. It's a managed service for running relational databases in the cloud.
Managed, meaning AWS handles a lot of the admin.
Exactly. Patching the OS and database engine, backups, scaling high availability setups, AWS manages that heavy lifting. It supports popular engines like MySQL, PostgreSQL, MariaDB, Oracle SQL Server, and Amazon's own Aurora.
Aurora.
Yeah, Aurora is Amazon's MySQL and PostgreSQL compatible database engine built for the cloud, often offering better performance and availability.
So RDS makes running databases easier. Where do they live?
They run inside your VPC, just like EC2 instances. You control network access using security groups.
Okay, what's the trade-off versus running my own database on EC2?
The main thing, as the sources point out, is you don't get operating system level access or root access on RDS instances. AWS handles the underlying machine. If you absolutely need that low-level OS control, you'd run the database yourself on EC2.
Less control, but less management overhead.
That's the balance. And RDS offers deployment options like multi-AZ for automatic failover to a standby in another availability zone, which is great for high availability. Security best practice, launch RDS in private subnets, don't give them public IPs.
Private subnets for databases. Makes sense. Okay, great overview of those foundational services. Now, let's revisit storage. We talked EBS for block storage with EC2, but then there's S3, simple storage service. How is that different?
S3 is fundamentally different. It's object storage, not block storage. It's designed for the internet, massively scalable, and you interact with it via API calls or web interfaces, not like a local disk.
Object storage, what does that mean compared to block storage like EBS?
In block storage, EBS, like a raw hard drive divided into fixed-size blocks. The operating system manages files on top of that. It's good for things needing frequent random reads and writes, like databases or OS file systems. Object storage, S3, treats data as complete objects. Each object contains the data itself, metadata, descriptive information, and a unique ID. You store and retrieve the entire object. It's not typically mounted like a drive.
So not like a file system directly?
Not directly, no.
Yeah.
It's better for storing large amounts of unstructured data. Photos, videos, backups, log files, static website assets, data that you usually access as a whole unit.
Got it. And S3 is big.
Massively big. You can store virtually unlimited amounts of data. Individual objects can be up to 5 terabytes. It's designed for extreme durability, like 11 nines of durability, meaning data loss is incredibly unlikely.
11 nines. Wow. So key advantages of S3.
Yeah, the sources list several. It's great for distributed apps, generally cheaper per GB than EBS, hugely scalable and durable, no limits on total data or metadata size per object. Ideal for data growth, backups, data lakes, static content hosting.
And where does the data live? In buckets.
Exactly. You create S3 buckets, and each bucket lives within a specific AWS region you choose. The data stays in that region unless you explicitly set up replication.
And who owns the bucket?
The AWS account that creates it. Ownership can't be transferred. And within that region, S3 automatically stores your objects across multiple availability zones for that high durability.
Buckets in regions owned by the account. Super durable.
Okay. We've covered a ton of services. Let's zoom out. Why AWS in the first place? The sources talk about market advantages.
Absolutely. There are the classic cloud advantages that AWS pioneered. Trading capital expense, buying servers for operational expense, paying as you go. That's huge.
CapEx to OpEx. Yeah.
Benefiting from massive economies of scale, AWS buys hardware in bulk, so it's cheaper. Stopping guessing capacity, you can scale up or down automatically. Elasticity.
Speed and agility, too. Right?
Definitely. Provisioning resources in minutes instead of weeks or months. Not having to run your own data centers, that's a massive operational relief. And going global instantly by deploying in different AWS regions.
Those are the big 6 cloud advantages. What about more specific benefits businesses see with AWS? Well, our sources point to things like reduced staff time for deploying new stuff, which means faster time to market for features. Dev teams become more productive because they get resources on demand.
No waiting for hardware.
Right. No managing the underlying infrastructure, no complex capacity planning. That elasticity and agility translate directly to business value. Lower costs overall because of the scale, and that global reach is a major enabler for many businesses.
So speed, cost, scale, global reach. It all adds up. Okay, let's wrap this up. We've covered a lot of ground today.
We really have. We started with EC2 virtual servers, talk instant store versus persistent EBS storage. Then IP addresses private, public, and the static elastic IPs. Network security with security groups at the instance level and NACLs at the subnet level.
Right, then encryption with KMS managing those keys. And the foundational services, SNS for notifications, SQS for queuing.
CloudFront for content delivery, Route 53 for DNS, and RDS for managed relational databases.
And finally, we contrasted EBS block storage with S3 object storage and looked at those overall advantages of using AWS.
Yeah, it's a foundational tour for sure. Each one of these services has way more depth we could get into.
Absolutely. This was really just scratching the surface, but hopefully it gives you, our listeners, a solid starting point for understanding these core AWS building blocks.
The real power comes when you start combining these services, right?
Mm-hmm.
Building applications using EC2, RDS, S3, maybe some Lambda triggered by SNS.
Exactly. Thinking about how these pieces fit together to solve problems, that's where the fun really begins. As you dig deeper into AWS, keep thinking about these core services and how they interact. What could you build by mixing and matching them?
The possibilities are pretty vast.
They really are. Well, that brings us at the end of this deep dive into AWS fundamentals. We hope you found it useful and insightful.
Yeah, thanks for tuning in.
Thank you for joining us today, and we'll catch you on the next deep dive.